Hello engineers, this is Shraddha Bharti and let's continue with our chapter on shear force diagram. In the previous lecture, we have learned about how to draw a shear force diagram. We have already cleared our confusion about the sign conventions. What exactly is the sign convention for the shear force diagram? We have also learned about whether to analyze the beam from the left hand side or the right hand side. And we have also learned about what are the good practices while drawing a shear force diagram. Now, in this lesson, what we are going to do is we are going to learn how to draw a shear force diagram for cantilever beams with the shortcut method. Okay, in this lecture we are not going for the conventional method because it is already available in most of the books. We are going for the shortcut method. This will help you to analyze the beam quickly for the competitive examinations. Now let's start with the first question. A cantilever beam of length L is carrying a concentrated load W at the free end. Now this is the same question which we have dealt with in the previous chapter, and in the previous chapter, I have solved this question from the right hand side as well as from the left hand side of the section. And also, I have used the conventional method and the shortcut method for solving the question. So, if you haven't seen the first lecture, please, I would request you to please go through the first lecture first. Okay. So, here is the concentrated load W, and we have to draw the shear force diagram. So first we'll cut a section like this. Let this section be XX. Now, if you look carefully, how is the load trying to rotate the beam about this section XX? Just forget about this part and look at the section this. The load is trying to rotate the beam about XX in the clockwise direction. Okay, so the shear force which we'll get will be positive. If you cut the section YY anywhere in the beam, same case will happen. The load will try to rotate the beam about the section in the clockwise direction. So same thing goes here. Now our shear force diagram will be a straight line, as when there is no loading in the beam, the shear force diagram is a straight line and it will be positive. Along with its magnitude will be W. And don't forget to write the sign convention. What am I doing is, my sign convention is this, though this is not a conventional method. Okay, let's go to the next question. This is a beam having concentrated loads. We have to solve this. We have to draw the shear force diagram. Now the confusion lies. We have to solve the diagram from the left hand side. That means from analyze the beam from here or from here. So one thing is that if you analyze the beam from the left hand side, that is from the fixed end, you have to calculate the reaction at the fixed end. So this will create an extra step. So we will shorten the question, will not analyze the beam from the left hand side, so as to we don't want to calculate the reaction at A. We don't have to calculate that. Let's continue. So let's cut a section here, XX. Suppose this 500 Newton is trying to rotate the beam in the clockwise direction about XX. If you move the section XX over here, same thing will happen. And if you move the section over here, same thing will happen. So as far as the section is moved between this part and this point, 500 Newton is trying to rotate the beam in the clockwise direction. Okay, so it will be positive, and the magnitude will be how much? The magnitude will be whatever is in the right hand section of the beam. Whatever is in the right hand section of the beam, 500 Newton. So this is 500. Now you next cut the section over here. Let's suppose section 22. Again, in section 22, what will happen is 800 Newton and 500 Newton are trying to rotate the beam in the clockwise direction about the section. So again, the sign convention will be positive. And what will be the magnitude? The magnitude will be now 500 plus 800, that will be 1300. So here it will go up to 1300. The magnitude here will be 1300. This is also positive. Now, if you cut a section over here, 3 section, and look carefully to all the loads on the right side of the section. All the three loads, that is 300 Newton, 800 Newton and 500 Newton, are trying to rotate the beam in the clockwise direction about section 3. And what will be the magnitude then? Magnitude will be 300 plus 800, that is 1100, plus 500, that is 1600. So again, I'll draw something like this. This is 1600, and the obvious thing is, if you cut a section over here, 4, so section, again same thing will happen. 1600 plus 400 will be 2000. So here the magnitude will be 2000 Newton. So this is the shear force diagram for this beam. So points you can remember over here is, the shear force diagram is constant when there is no loading in between the sections. And when there is a sudden loading in the beam, the shear force diagram jumps suddenly. See this, 1300, 1600 and then 2000, they are all the points where the point load is acting. This is the point where the shear force diagram changes suddenly. So these are the points which you can remember. This will help you to analyze the beam very quickly. So 2 points over here, when there is no loading in the beam, when in a section the shear force diagram is constant. When there is a point load acting or the concentrated load acting, the shear force diagram jumps quickly. We are moving to the next question. A cantilever beam of length L carrying a downward load P at the free end and the upward load P at a distance A from the free end. So there is a figure over here. Downward load is acting over here and upward load is acting over here. There is a distance A between them. What we have to do, we have to draw a shear force diagram again. We cut a section as usual. Let this section be 1, 1. Now, this P is trying to rotate the beam in the clockwise direction along the section 1, 1, right? And its magnitude will be how much? P only. So it will be positive. Now, if you pass this loading and cut a section over here, let this section be 2, 2. And if you see this beam is trying to rotate the section in the clockwise direction, while this load is trying to rotate the beam in the anti-clockwise direction, both with the magnitude P, right? So overall, if we add up this force and this force on the right hand side of the section, what will happen? One is P, one is minus P, this is 0. So there will be no shear force acting at the section 2, 2. So what will be the loading diagram over here? The loading diagram will be just this one, and there is no load over here. So this is our shear force diagram for the given loading diagram. So one thing to analyze over here is, when a downward load is acting, the shear force diagram is in the positive direction. Now one upward load is acting over here. One upward load is acting over here. So the shear force diagram went by a magnitude P in the downward direction. Okay. So this is the key point which you can remember for even faster analysis of the beam. When there was a loading which was acting on the downward direction, the shear force diagram jumped with a on the positive direction with a magnitude P. Now the same thing happened when the loading diagram is in the positive direction, that is in the upward direction. The shear force diagram jumped downward with a magnitude P, and there is no loading over here, so there is no loading, no shear force over here. Let's move on to the third question. So the question says there is a slanting load P which is acting at an angle of 30 degree or say theta degree at this point of the beam, and the beam is of length L, and we have to draw the shear force diagram. How to do that? So let's cut a section over here. Can you see any loading on the right hand side of the section over here? There is no loading, so there will be no shear force over here. Similarly, if you move the section till this point, there will be no shear force. Now what will happen at this point? The load is slanting over here. So as we know, the load is having two components. One should be in this direction and one should be in this direction. So the horizontal component of the force is having no effect on the shear of the beam. It is just compressing the beam in the axial direction. So it is having no effect on the shear force. While this component, that is the vertical component, which is P sine theta, is causing the shear force. Now if you cut a section 2 to over here, and if you see carefully, this P sine theta is trying to rotate the beam in the clockwise direction at the section 2. So what will happen? What will be the shear force diagram over here? The shear force diagram will be constant, as there is no loading between the load and the fixed end of the beam. What will be its magnitude? Its magnitude will be P sine theta, and I'll write what sign convention I have followed. So this is not a very authentic method of drawing the shear force diagram. If you are a college student and you have to give the university exam, you cannot draw the shear force diagram like this, okay? Because you have to show the steps. Now, how exactly to show the steps? That you will get in the lecture 1. So I would request you, if you are a college student and you want to give the university exams and you want to learn how to write the steps for the drawing the shear force diagram, lecture 1 will help you out, okay? So here comes the next question. A cantilever beam of length L carrying a uniformly distributed load of W Newton per meter over the whole length of the beam. Now here comes a question where the loading is not concentrated, rather that it is uniformly distributed. What does it mean? It is W Newton per meter. For each meter, it is having an intensity of W. So let's do the same thing. Let's cut a section over here. Let the section be 1, 1. Now, how much will be the loading over here? If the distance is x, suppose, if the distance is x, the loading will be W into x. It is for 1 meter, it's W. For x meter, it will be W into x, right? If we concentrate on the extreme right point, there is, suppose in the extreme point, there is no load to cause the shear. So the loading will be 0. And in the extreme left, how much will be the loading? It will be W into L. Why W into L? Because the length of the beam is L and W is the intensity of loading. So it will be W into L in the left end. And the shear force is varying in a linear fashion. Linear fashion means like this. And it will be positive again because all the loading is trying to rotate the beam in the clockwise direction whenever we cut a section. So this will be the loading diagram for a UDL. Now you notice one thing. I have told you when there was no loading in a span of beam, as in here, in this case here, suppose the shear force diagram was constant. But in this case, in the case of UDL, the shear force diagram is linearly varying. In case of UDL, what happens is the SFD varies linearly. Varies linearly. So these are the points which you can remember, and this will help you to analyze the beam very quickly. In case of UDL, the beam varies linearly. In case of concentrated load, there is a sudden change in the shear force diagram. Either it jumps upward or downward, or when there is no loading in the beam, the shear force diagram is constant. Now, a cantilever beam of length L carrying a uniformly distributed load over the whole length of the beam and a concentrated load W at the free end. Now, what we can do is we can apply the principle of superposition. Now, what is this principle of superposition? Principle of superposition says that we can analyze the beam considering it as two different beams. So one beam is containing this concentrated load. We have already drawn the shear force diagram for this. And the second beam is containing a UDL like this. Now we know that the shear force diagram for this one is like this. We have already done that. And the shear force diagram for this one is like this, right? In the previous question, we have done this. If we apply both of them, we'll get the shear force diagram for this beam. So the concentrated load is capital W, let's suppose. So it will be capital W here. It will be capital W all along the beam. Now, for the linear variation, it will be like this. So here, what will be the shear force at this point? It will be capital W from here. It will be capital W plus small w into L, length of the beam. Okay. So this is all positive. Now you have understood about the pattern of the beam. You can quickly solve this question. There is no loading in the beam over here, so there will be no shear force diagram. If you cut the section anywhere between this, so what will happen? The load will start increasing. And since this is a UDL, the shear force diagram will be, the shear force diagram will vary linearly. And this will be the shear force diagram. I hope this is very much clear to you. We'll quickly solve this one. A cantilever beam of length L is carrying a UDL for a distance A from the fixed end. So this distance is A and this distance is L. So here the magnitude will be W into A. Similarly for this one, if you cut a section, you will get a UDL, and for UDL the shear force diagram varies linearly, and it will be positive in direction. Why it will be positive? Because there is the loadings are acting in the downward direction, and I have taken the uh, sign convention as like this. For this point up till now, it's clear. This magnitude will be W into A because this distance is A. Now, what will be the loading diagram here? Will it be zero? There is no loading. Will it be zero? No. All the forces for the UDL is trying to rotate the beam in the clockwise direction here also. But since there is no loading, the shear force diagram will remain constant. It will not increase any further. So the shear force diagram will remain constant for this section of the beam. So as I've told you, when there is no loading in the beam, the shear force diagram remains constant. When there is a UDL in the section of the beam, the shear force diagram varies linearly. So this is another question. Cut a section, 2.5 Newton. 2.5 Newton means 2.5 like this. It is trying to rotate the beam in the clockwise direction. Now, it is 1 Newton per meter. It will start in from this point, the loading will start increasing. So it is 2.5 over here, 2.5 over here. It is 1 Newton per meter for 2 meters. So it is, how much will it be? So 2 Newton will add. So it will be 4.5. Total will be 4.5 Newton. Okay. Now there is no loading in this portion. So the shear force diagram will remain constant. Now there is a downward load again. So if we cut the section, this load, and this load all will try to rotate the beam in the clockwise direction. And as I have told you, there is a load, there will be, as there is a load, there will be sudden jump in the shear force diagram by a magnitude of 3 Newton. So 4.5 is here, 4, 5, 6, 7. So it will be 7.5 Newton. And again, then it will be constant. So I hope you have already learned how to draw a shear force diagram with number of questions practiced in this session, and you have liked the session. So please don't forget to share, subscribe to my channel. And this question is one of the difficult question which must be understood separately. So I create a separate video for this loading diagram, and it is one of the most important thing. So thank you guys for your patience. Hope you like this lesson. That's all for today's class. See you in the next lecture. Bye bye and have a nice day. Don't forget to like and follow me for more. And uh, if you want to go to the basics, do watch the first lecture first. Okay. Bye bye and have a nice day.